Okay, so this is the last lesson in Unit 2. This lesson is on the intermediate value theorem. And when this theorem is written out in words, it sounds kind of confusing. So I'm going to try to kind of explain it in common sense words, okay? So the first thing that's very important is that we have to determine that the function we're talking about is continuous. As long as it's continuous on the interval that we're looking at, okay? It says that any number between f of a and f of b, all right, so here's f of a and here's f of b, and here's a number in between them. Then there has to be a number between a and b, a number c between a and b. So here's a and here's b, here's a c, where that's the function value. Okay, so all we're saying is, if you pick a number between these two, that the answer has to be between these two. There has to be a place between these two where the function value is between these two. Okay? So here's a little example solved out for you before we get into the full note. So this, you have to always start by verifying that the thing you're looking at is continuous. This is continuous because it's a polynomial. All polynomials are continuous. So what they're saying is, if you do f of 0, you get 4. If you do f of 5, you get 24. All right? 10 is between those two values. So I'm just saying that between 0 and 5, there has to be an answer to that equation, that function value equal 10. There has to be one solution in this interval that makes this true. And so I solved it out, and you see I got 3 and -2. 3 is in this interval, okay? So it's kind of weird. It's an existence theorem. It doesn't tell you how to find something or what to find. It just tells you that there has to be an answer in this interval to this equation, because 10 is between that 4 and that 24, that there has to be an answer in this interval, okay? It's a little weird. And then the same thing works here. This is just saying that, same idea, that if the function value goes from negative to positive, that it must have been 0 in between there, because 0 is between a negative and a positive, okay? So you do a little bit with the positive to negative, I think, in pre-calculus. So this just kind of extends it to any number. Like if it's between 4 and 24, 10 is between 4 and 24, it must have been 10 somewhere in between there. All right, so in simple words, if a function value goes from, say, 1 to 7, somewhere in between there, it must have gone through 6, right? Say if it goes from -2 to 5, somewhere in between there, it must have gone through 0. All right? So this is the theorem stated formally. And again, the formal definition sounds confusing sometimes, but it has to be continuous on the closed interval. If k is a number between f of a and f of b, and I'm marking it on this picture to kind of help it make sense to you, then there has to be one value c in the open. Notice that the original interval was closed. This has to be open, which means it can't be the two endpoints. There has to be one number c between a and b where f of c is equal to k. I think it makes more sense when you look at the picture at the same time. All right, so we're going to do a few examples. This first one, it says use the intermediate value theorem to show that the equation has at least one solution in the given interval. Okay, so first of all, you have to state that this is continuous. Reason, it's a polynomial, and that's enough. Okay. We're talking about the interval 0 to 1. So you're going to start by evaluating that function at 0, this f of x, this part, okay? So f of x is this side of the equation. F of 0 is 0. And f of 1, if you plug 1 into that yellow expression, you should get 4, right? It's 1 to the 5th plus 4 times 1 squared minus 1. That should be 4. So at 0, it's 0. At 1, it's up at 4. Okay, we don't really know what this function looks like, but we do know that it's continuous. So we know that it has to like not have any gaps in between there. And so we want to know, is this thing equal to 3 on this interval? So here's 3, right? So the answer is yes. All right. So it's a little wordy to state your reason. So we're going to say since 3 is between the 0 and the 4, so since 3, this is like a math term, means is an element of, so it's in the set 0 to 4, there must be, and you have to say at least 1. Oops, I wrote a T instead of an L there, sorry. There has to be at least one value of C. In the open interval 0, 1, where f of C is equal to 3. Okay? So there's the first example. The wording is so you have to, I'm going to kind of highlight this. So you have to start by saying that it's continuous, right? And then you have to say that the value you're talking about is between these two. Since 3 is in this interval, there has to be, and you have to state at least 1. That's important. And then that C value has to be in the open interval of what you were started with. Okay? So let's try another one. Again, you always have to start by making a continuity statement. So this is a rational function. Rational functions are continuous where they are defined. So this function, if you take the denominator and set it equal to 0, and solve that. All right, so this is defined for all real numbers, therefore continuous. I can't read what I'm writing here. Sorry. Therefore continuous for all real numbers, okay? So we have our continuity statement. We know that it's continuous. So now we're going to do f of 0. If you plug 0 in there, you get 7 over 1, which is just 7. And if you plug 2 in, you get 2 squared is 4. 4 plus 7 is 11 over 5. Which is 2.5. Okay, so the next thing we're looking at is 5 between these? It is. So now we're kind of ready to write our statement. So, sorry. We got to write since 5 is in the set 2.5 to 7, there must be at least one value of C in the open interval 0 to 2 where f of C is equal to 5. Okay, and on this one you can look at it graphically if you want. Also, f of 0 is up at 7, and f of 2 is equal to 2.5, which is like here. We know it has to be continuous, so there can't be any gaps in there. And so the question is it equal to 5 somewhere in there? Which 5 is like here? Well, yeah, it does have to be equal to 5 in there, right? It's got to be equal to 5 at some point. All right, so let's move on to the next one. All right, so this one, rational functions are continuous where they're defined. So this one, the denominator is equal to 0 where x is 3, okay? But 3 is not in this interval, okay? So we're gonna write f of x is undefined at x equals 3. 3 is not in the interval -1 to 2, therefore continuous on that closed interval -1, 2. Okay, so there we have to start, always have to start with our continuity statement. It is continuous. All right, so now we're going to go ahead and, so f of x is your x squared minus 9. F of -1 would be -8 over -4, which is +2. And f of 2 is going to be -5 over -1, which is 5. Okay, so now we're saying that 4 is between 2 and 5. Therefore, there has to be one solution to that equation between -1 and 2. Okay, so we're going to write since 4 is in the interval 2 to 5, there must be at least one solution, at least one, value of C in the open interval -1, 2. It can't be the endpoints. Where f of C is equal to 4. Okay? And so that orange is this, right? 4 is in there. There has to be a C in this. All right, the next one. Using the intermediate value, just one solution on the given interval. So this one, almost the same problem, but it's a different interval. All right, so again, x minus 3 is equal to 0. So f of x is undefined at x equals 3, and that is in this interval. All right, so f of x is discontinuous. So I'm going to write since f of x is discontinuous on the closed interval 0, 4, the intermediate value theorem is inconclusive. All right. And the last two are that special situation where it goes from negative to positive or positive to negative, and if it changes sign, then it must have been 0 at some point in between. Okay, but again, it's so important, you still have to state that it's continuous. So this is continuous because it's a polynomial. All right, so our f of x is that function, f of 0 is -1, and f of 1 would be 1 plus 2, which is 3, minus 1, which is 2. All right, so we're going to write, since there is a sign change, there must be at least one value of c in the open interval 0, 1, where f of c is equal to 0. And the last one, this one we want to show that there are actually 3 distinct zeros. Okay? So again, we're going to start by stating that this is continuous because it's a polynomial. You can put that right in your, just plug all these values in and write down what they are. So f of -3 should be -53. At -2, it's -19. -1, it's -3. 0 is 1. 1 is -1. 2 is -3. And 3 is 1. All right. So we're going negative to positive, positive to negative, negative to positive. Okay? So since there are 3 sign changes, there must be 3 values of c in the open interval -3, 3, where f of c is equal to 0. 3 sign changes, 3 values of c where the function is 0. All right, and so that concludes Unit 2.